I'm Dr. T, and welcome to my office. Today I'd like to talk about heat and what happens when you start moving it around. So one of the first things we can start thinking about when something starts to heat up, especially if it's something that, it's like water. We sometimes see it as a solid or a liquid or a gas, and that is a phase change. So let's actually dive in and think a little bit about this. So when you've got a solid, it's going to have atoms that are kind of bouncing around a bit, but kind of staying in pretty tight. And then the more heat you get, the more they're going to kind of bounce around a little bit more and more. And for most substances, that's actually going to cause it to get a little bit bigger, thermal expansion. But at a certain point, now they're going to have enough energy that the forces that hold them together, what we call intermolecular forces, aren't able to hold them in place. So now they're going to start sliding past each other, and this is a liquid, so we are melting. Or, if you're the Wicked Witch, melting! Sorry, bad joke. Anyways, as they're doing this, of course, yay, we're using energy to break the bonds holding the atoms together, and it starts to melt. Now this, if you're looking at it and you're looking at the temperature, something really interesting happens. While you're adding heat, before it starts to melt, the solid is going to go up and up and up in temperature based on the calorimetry equation up there. But once it starts melting, and you'll have some imperfections where some of it won't quite have gotten up to temperature yet, and but for the most part, and it's surprisingly good how for the most part actually works. It won't raise in temperature. The temperature will just hold constant unless you've done something kooky with your thermometer and put it too close to the hot plate. The substance doesn't warm up. All of that heat goes into melting it. So you can actually start plotting this, and you can plot, time or the amount of heat you add on the x-axis, temperature on the y, and you'll get what we call a heating curve, and it goes up nice and linear. Assuming you mix, and then it will go flat. And while it's flat, that's when it's doing the phase change. And then it'll start going up again in a nice line. New specific heat, because it's now a liquid, not a solid, and that will warm up until it reaches its boiling point, at which point it goes flat line, and it just, all that heat goes into it until it warms up. This is why you can't heat water past its boiling point and still be water. There's ways of cheating. The boiling point is controlled by the pressure. So if you have a pressure cooker or an Instapot, which is a cross between a pressure cooker and a crock pot, weird. In those cases, you know how they latch on the lids, that builds up a high pressure so you can raise the boiling point, therefore you can cook hotter. But you can take advantage of this with like a double boiler, and that way you know that the bottom of your top pan, the one that has the chocolate in it or whatever delicate material you have, can't go above the boiling point of water because the water won't go above that boiling point. Now, of course, once you're into gas phase, you can now heat the steam up hotter and hotter and hotter, and a lot of industrial applications will use superheated steam. It's great for driving power mills. If you look at a power plant or a boiler, that's all superheated steam. That's not normal steam. That's really hot steam. As I'm talking about this, I should also point out that there are certain substances like carbon dioxide that under some conditions will skip the whole liquid part. So dry ice is called dry ice because it sublimates. It goes from a solid straight to a gas. It doesn't melt or boil, and typically we actually call vaporizing, not boiling, but same concept. And then, if you were to cool it back down, it would skip the liquid phase again, and what we call deposition, going down and cooling straight into a solid. Now, when it comes to this moving heat, we can use it to our advantage. And I kind of alluded to this earlier with boilers. We can have what's known as a heat engine. So a heat engine takes advantage of the fact that heat will always travel from the hot part to the cold part. Or at least I should say, will always spontaneously travel. You can force it to go the other way. You can use energy to make the heat go from the cold to the hot. That's how your refrigerator and your air conditioner work. But a heat engine is any device that's going to take advantage of the fact that the heat wants to go from hot to cold, and then take that heat and do work with it. So of course you can imagine, your car or a boiler or something like that. You're taking this disorderly form of energy and you are siphoning some of it off into an orderly form. Well, it's usually said 3 laws of thermodynamics. It's actually 4, so it's 0, 1, 2, and 3. I'm going to look at the first 2. So the first law of thermodynamics basically says that you can't get any free energy. All of the energy change for the universe, so everything combined, is going to be the sum of the heat and the work. You can't get more work out than the energy you put in. So if I've got some coal and I burn it, I can't get any more energy out of that coal than what came from that coal. So no free energy. The second law of thermodynamics basically states that you always have waste. You always have heat that escapes and you can't use. So the first rule is you can't win. The first rule is you can't win. The second rule is you can't break even. The other 2, I'll let you look them up, but they're a little bit more technical in nature. The first 2 are the ones you really want to focus on. Heat engines, definitely a useful thing, and boy, those rules of thermodynamics, they are annoying. That's why there can't be a perpetual motion machine, sadly. Boy, those would be nice. You can have very efficient machines, ones that can run for very long times, but not forever, and if you try and take any energy out, well, you only have so much to start with. So with that said, have a wonderful day.